How's the homework going? Any problems on any of the 2D rigid body statics? Yeah.
I actually have something on statics.
Oh, well, I can't talk about that in statics. Yeah.
I just have one quick question.
Yeah.
On the weekly assignment for problem 1, when it says find 2 that means just the positive and the negative.
Yeah, you can think of it that way, right? Yeah, exactly. One's going one way and one's going the exact opposite.
Okay.
Yep. Okay, well, we've done 2D joints, so now I'm going to list out the 3D joints. I don't know if hopefully I'm going to get through them today, but it's a little, there are more different types because now you have 6 degrees of freedom to play with instead of 3. So, okay, 3D joints. So remember, in 2D, a body without restrictions on its motion has 3 degrees of freedom. So if this is the body, it can move along a line, along a perpendicular line, or it can rotate in the plane. Okay, so those are the 3. So 2 of these are translational. And this one is rotational. In 3D, what is that, a B? I spelled 3D with a B. 3D. Okay, so here is the body. So there are 3 directions of translation that are perpendicular to each other. And then there are also 3 axes of rotations. You can have a rotation around that axis, around that axis, and around that axis. So now we have 3 translational degrees of freedom and 3 rotational for a total of 6. You know, add them all up, 6 degrees of freedom. Remember in 2D, the number of Newton's laws we had corresponded exactly the number of degrees of freedom. So we have two components of Newton's second law and 1 component of the moment equation. It works out the same way in 3D. We have 3 components of Newton's second law and 3 moment equations, 3 components of the moment equation. And it works exactly the same as it did in 2D. If a translation is restricted, the joint applies a force. And if a rotation is restricted, the joint applies a couple. So in 2D, I went through, I called them the categories. Each category was the number of variables that the joint introduced. And we started with the joints that introduced one variable, and then we went up to the maximum you could have in 2D, which is 3 variables, because that's all the equations we have. So now we're going to start with 1 variable, and we have to go all the way up to 6. And some of them get a little trickier to understand in 3D. Man, I do have a bunch of those 3D models of joints, but I didn't bring them. I guess I forgot to bring them. But email me if you want, if you have trouble understanding any of this stuff. Let's set up a time to meet at office hours or outside of office hours, and I can show you the physical joints and show you how the motion's restricted. And I think it helps if you get to hold it. And, you know, it's not quite as useful for me to use it up here anyways, as it is for you to look at it and feel like, okay, you can do this, you can't do this. Okay, so joint category 1. So just like in 2D, these are the ones that apply a force with a known direction. Known direction. Come on. And they introduce 1 variable into the equations. There are 2 of these. The first one is a frictionless contact. So a free body diagram of that Olive Garden breadstick. Is a force that's perpendicular to the surface of contact. So like that. What do we know about N? N must be positive. Otherwise, the surface would be pulling down on the object. The second one of these is a roller. And we're talking about a roller with no preferred direction, like a ball roller, not a wheel. A wheel has a preferred direction, so we'll get to that in a second. And so a free body diagram of that body. The force has to be perpendicular to the surface of contact. At force N, can that be positive and negative or just positive? Yeah, it has to be positive, right? Okay, so those introduce one variable. So with those, you're gonna have to do a lot of work to get up to constraining all 6 degrees of freedom for this to be in static equilibrium. And so now we're on to category 2, the ones that introduce 2 variables. And all of these, oh, there's only one of them. Oh, there's only one, I think, from now on in all of these categories, because we're working our way up to 6. This force, or this joint, applies force components in 2 directions. And introduces 2 variables into the equations. And this is a wheel with a preferred direction. So this is the other kind of roller you can have. That's right. And so free body diagram. There's a normal force that's perpendicular to the surface of contact. And then there's also a force these two are perpendicular to each other. Are you with me on what that's supposed to be? So this is a normal force. And this force F is what keeps it from sliding out of its preferred direction. It's friction. Yeah, so we're not ever really, until the end of the class, we're not going to deal with coefficients of friction because it's static friction again, and so it would just give us limits, and so we're just going to use it as a fully unknown force in that direction, and we'll calculate the value. Question?
I was going to ask, is it still normal, like a moment?
No, there's no moment yet on either of these. Because if you think about the directions, well, You could possibly argue that it's prevented from rotating about the vertical axis, but we're going to ignore that too. And it's definitely free to rotate side to side, and it's definitely free to rotate front and back. If you've ever been on a unicycle, you're well aware of that. Any questions about that one? So N has to be positive in this case. F can be either direction. Okay. Joint category 3. This is an easy one. 4 and 5 are tricky, the two trickiest ones. So I want you to appreciate the simplicity of this one while it's still around. So category 3. This is a single joint, and it's a force with an unknown direction. So a full three-dimensional force vector. And this introduces 3 variables. And this joint is a ball and socket joint. The joint that we're going to deal with most in 2 dimensions is a pin joint, like a hinge. In 3 dimensions, it's a ball and socket joint. Okay, this is what we're going to see the most. And it looks something like this. So 1 is the top. At the point where those 2 pieces articulate, there's no translation in any direction. That's why it applies a full force vector. But any rotation is allowed. So that top piece can, well, think of, my elbow can sort of work that way. So it can rotate about this axis, or about this axis. Okay. So that's why there's no couples applied. We haven't seen any couples for any of these yet. And I'll write this force vector as the force on body 1 by body 2. If you did a free body diagram of the lower thing, it would look like that, but the force vector would be negative F12 because of Newton's third law, or F21. And all these components can be positive or negative. Okay, now we're getting into the 2 more complicated ones because what they do depends on how they're being used in the problem, in the design. So category 4. This introduces up to 4 variables. It applies 2 force components always. and two couple components sometimes. That means that it introduces two or four variables, depending on the setting. What? That's right. It's either it applies couples or it doesn't. Okay, and this is a pin joint without thrust. Thrust is a force along the axis of rotation. All right, so there's one of the bodies that's connected. Let's say these bodies are connected by sort of an exaggerated pin going through them. Okay. You get the gist of what I'm trying to draw there? I'm going to put a coordinate system on this. I'm going to make the y-axis point along that body, the z-axis along the axis, and that means that the x-axis points this way. The idea of thrust is, so if these two bodies can both slide along that long pin, okay, say that they can slide freely along that, then that pin isn't applying any force along the axis of rotation. And so that's what it means for a joint to not provide any thrust, okay? A lot of times you'll see these acting in pairs, and there'll be one that doesn't provide thrust on one side and one that does provide thrust on the other side. So if this is body one, a free body diagram of body one looks like this. So there is a force vector applied along the x-axis because that body can't translate through that pin. Okay. So I'll call that Fx. And there's a force vector applied along the y-axis. Because again, that body can't translate up and down through that pin. There's no z component because that body is free to slide along the pin. Yep.
So if it isn't, then it's
Right. If it's so that's the next one we'll talk about is a pin joint with thrust, and then you'll also have a z component of the force. And in that case, there'd have to be some kind of flange or something on that pin that prevents the motion. And now the couples. Think about the couples. If this bottom member is fixed, welded to the ground or whatever, what ways can that top member rotate? Well, we know it can rotate about z, so there's no couple in the z direction, right? What about x? Could it rotate about x? That would be like, couldn't do that. And could it twist about y? No. So we also have x and y couples. And I'll write those as these double arrows. And so this is fx and mx and fy and my. And those are the four. And these are perpendicular. Okay, so when don't you have, so this is the 4 variable case. When do you only have the 2 variable case? Ignore the couples. When 2 pin joints are oriented along the same axis. So if you have a body like this, and it's connected to the wall, so that's supposed to be a hinge. Okay, if there's only one of those like that, and say that this for some reason doesn't provide any thrust, I guess the way I've drawn it, you would think that that would provide some thrust. But the way it is there, it would provide those 2 couples. Okay, you can't twist this thing or twist it like a frisbee. Okay, but if we have another one of these here, shares that same axis, then notice that there's no need for those couples to be applied, for those rotations to be prevented. Like what prevents this from rotating like a frisbee? That other, we're not relying anymore on the left one applying a couple. Now that one on the right can just apply a force that keeps it from rotating. Okay, and the same thing with it twisting this way. You know, we don't need to rely on either one of those individual joints to apply a couple because the other joint can just apply a force. You'd rather not rely on pin joints usually to provide these couples. If they're small, like okay, but if they're big, you know, I mean, imagine like if your job for the day was breaking this joint apart, the first thing you would do is try to make it apply couples. That twisting motion is how you would break this thing, right? And so you'd rather rely on these pin joints to apply just forces by putting 2 of them together along the same axis. Okay. Okay, now we're on to category 5, and this is just the same thing, a pin joint, but this time it does have thrust. So this applies 3 force components, or a force vector with an unknown direction. And how did I say this before? Oh, and this is, so 3 force components always. And 2 couple components sometimes. And so this introduces either 3 or 5 variables. And this is a pin joint with thrust. So I'll draw that as having flanges on both sides like this. With a pin through here. You follow what I'm trying to get at there? Again, let me know if you want to play with, I have 3D models of these joints, and you can see how it all works, see where the motions are stopped and stuff. All I got here is drawings today. So let's say our axes, coordinate axes are going to be a y-axis up, an x-axis out, and a z-axis along the pin. And this is what I'm going to call the body 1. Then the free body diagram looks like this. You have a force component along x, a force component along y, and a force component along z. So I'm going to just write that as a vector F12. And then you also have 2 couple components. Can I rotate about the x-axis in this without breaking the joint? No. Can I rotate about y? No. Can I rotate about z? Yeah, it should be, or it's not well lubricated. So there's no couple about z, but there is about x and y. Ignore the couples. Again, the same exactly as for a pin joint without thrust. If 2 pin joints share the same axis. And the last one is easy. This is just a fixed joint, because if you restrict all 6 degrees of freedom, the thing just can't go anywhere. So this is 3 force components and 3 couple components. And that means it introduces 6 variables. And this is a fixed joint or a weld joint. I'll call these axes Y up, X along the thing, and Z this way. And so a free body diagram you have a full force vector and a full couple vector. And I'll just call these, so if this is body 1, I'll just call this the force on 1 by, I'm going to say the wall is body 2, and the couple on body 1 by body 2. Yeah.
So, why don't the same group apply to the couples, the weld joint? Because if you had two of them fixed to the same wall.
Well, for doing statics, if you have more variables introduced than just a fixed joint, you can't do the statics anyways. So that just can't come up in statics. We currently don't have any way to deal, like if you have a, so imagine a,
Because we're out of variables.
yeah. So imagine a setup like this, and I'm going to draw it in 2D because I think it's easier to visualize. But imagine that you have in 2D a fixed joint and a roller at the end supporting this beam, and you're applying some force to it or whatever. Okay. In 2D, you only have 3 equations from Newton's laws, right? So you can only solve for 3 variables. The fixed joint introduces 3 variables, and the roller introduces 1 variable. So you have 4 variables, and you can't solve that equation. Now, that's a perfectly reasonable way to support that thing. You just can't solve for the forces by using only statics. And so in order to solve that equation, those equations, you need to also use stuff we learned in deform. Any other questions? Well, I'll do an example problem or 2 next time, but let's do the quiz, and I'll look. Maybe, I think you can do some probably free body diagram problems based on what we've done. Yeah, question?
I was just saying, so essentially it's X or the Z.
That's right. There's only one more variable. It's just that a pin joint with thrust still allows the thing to rotate around the pin, and this doesn't allow anything to happen. So one by one, we just kept introducing one more force, one more couple until we restricted all the motion. Would someone mind coming and handing these out? Thank you. Since I'm crippled.
Yeah, what did you do?
I don't know. I didn't do anything. I just. Really?
I mean, before the whole process.
Oh, yeah, that same uncle. That's horrible. Okay, I'm going to turn this.